Hello everybody, welcome back to ATM 5, Our Changing Atmosphere. In this lecture, we're going to lay some groundwork on the structure of the atmosphere, including its physical characteristics and composition. These facts will be needed for us to understand how and why energy moves around the Earth system. In this section, there are quite a few definitions. We're going to define the Keeling curve, troposphere, stratosphere, mesosphere, thermosphere, as well as tropopause, stratopause, and mesopause. The key questions addressed in this section are: what are the chemical constituents of the Earth's atmosphere? What are the most important constituents for the study of climate change? How has human activity affected the atmosphere's composition? What are the layers of the Earth's atmosphere, and how are they distinguished? And what are the characteristics of each layer of the Earth's atmosphere? First, some basic properties about the planet Earth. The Earth rotates on its axis once every 23 hours, 56 minutes, and 4 seconds. However, because it also moves a little farther around the sun each day, that makes for a 24-hour solar day. That is, the time between the sun being overhead for a particular observer standing on the planet is about 24 hours. Rotation is counterclockwise if viewed from above the North Pole, so the sun rises in the east and sets in the west. The Earth is tilted by 23.5 degrees relative to its orbital plane, namely the surface around which it orbits the sun. The equator here is shown in red. The North Pole points in the same direction regardless of where it is in its orbit, towards the North Star, aptly named Polaris. Since the tilt is not exactly perpendicular to the line connecting the Earth and the sun's position tends to move depending on the time of year, as observed by somebody standing on the surface of the planet. In this image shown here, the red line represents the equator, so the sun is overhead in the northern hemisphere in this particular image. Seasonal changes are purely due to where the Earth is in its orbit. In this image, the equator is shown in red, the tropics of Cancer and Capricorn in purple, and the Arctic and Antarctic circles in blue. On June solstice, also known as summer solstice in the northern hemisphere, around June 21st, the Earth is tilted so that its northern hemisphere is more exposed to the sun, and so in the northern hemisphere it experiences warmer temperatures. On December solstice, also known as the winter solstice in the northern hemisphere, around December 21st, the Earth is tilted so that its southern hemisphere gets more exposure to direct sunlight. Consequently, temperatures will be higher in the southern hemisphere. You can only experience the sun being directly overhead if you live or are staying somewhere between the Tropic of Cancer and Capricorn, and only twice per year. However, when it happens, it's actually known as Lahaina Noon in Hawaii, and gives rise to some pretty cool photos. I encourage you to check that out on Google image search. Going back to orbital scales, the distance between the Earth and the Sun is on average 149.6 million kilometers, or about 93 million miles, although its orbit is slightly elliptical. That is, it does vary somewhat from a perfectly circular orbit. During certain times of the year, the Earth will be slightly closer to the Sun than during other times of the year, but the variation is relatively small. Since the highest mountain on Earth is only about 9 kilometers, even being at the top of Mount Everest only brings you infinitesimally closer to the Sun. Think of it as a ratio of the 9 kilometers from the climb up Mount Everest compared to the 149.6 million kilometer Earth-Sun distance. So in terms of the amount of energy received, there's basically no difference between whether you are at the surface, the mean surface, or at the top of Mount Everest. Similarly, being at the equator makes no difference from being near the poles when it comes to your distance from the sun. That is, this is not the primary driver of equator to pole temperature differences. Variations in the Earth's surface height are also tiny compared to its radius. If you can imagine being shrunk down to being small enough that you could hold it, the Earth itself would actually seem as round as a billiard ball. Although it's not exactly smooth, your touch would still be able to feel the differences in the underlying topography, but the variation in the altitudes of that topography would nonetheless make the Earth very close to being a perfect sphere. The atmosphere is also really thin compared to the radius of the planet. You are considered to be in low Earth orbit, that is effectively space, if you reach an altitude of 100 kilometers. So if you buy a ticket on one of the space airlines for $10,000 or $100,000, I don't know how much they're charging nowadays, if they bring you up to 100 kilometers altitude, they can honestly say that they've brought you to space. For comparison, the International Space Station orbits at a distance of 410 kilometers from the surface. On the highway, assuming you're obeying a 60 mile per hour speed limit, if you're in the US, you would go about 100 kilometers in an hour of driving. So for those of us in Davis, that means San Francisco is farther away from us than outer space. Effectively, all the atmosphere's water and all the weather that's relevant to us occurs in a region of the atmosphere known as the troposphere, which extends to only about 10 kilometers altitude in polar regions and 18 kilometers in the tropics. The highest peak in the world is Mount Everest at 8.85 kilometers above the mean surface, reaching almost all the way to the top of the troposphere. So in this class, we're basically studying a very thin layer of gas that's less than 1% of the total Earth's radius. Nonetheless, it is a layer that is incredibly important to life on this planet. Air density at the surface is a little more than 1 kilogram per cubic meter. But much like a blanket, this atmospheric layer helps us keep warm, and as we'll learn, is responsible for making the surface a fairly comfortable 15 degrees Celsius, averaged globally, or about 58.7 degrees Fahrenheit. The total weight of gas above us in the atmosphere is nonetheless immense when you add it all up, equaling 5.79 quadrillion tons. At the surface, this gives us a surface pressure of 101,300 pascals, for those of you familiar with the physics unit. More concisely, in layman's terms, this can simply be written as 1 atmosphere. All right, let's turn our attention to discuss the chemical composition of the Earth's atmosphere. The atmosphere is not a single substance, but is composed of a mix of many gases. For this course, we need to know about the chemical composition of the atmosphere, since it plays a huge role in determining how energy moves around the atmosphere. I know many of you have learned about this earlier in your education, so let's see if you can remember the major constituent gases as we go through the list. By volume, nitrogen gas, or N2, is the most common constituent of the atmosphere, equal to about 78% of all molecules. Next comes oxygen gas, or O2, which represents 21% of the atmosphere by volume. Notably, oxygen is needed for combustion, so if oxygen was a higher percentage of the atmosphere, then fire would be a much more common problem worldwide. Together, these two gases already contribute to 99% of the total atmosphere by volume. Next comes argon, which is oft forgotten as the third most abundant component of the Earth's atmosphere, and generally forgotten, of course, because it's largely unreactive and unimportant for our climate studies. It represents 0.93% of the total atmosphere by volume. After argon comes water vapor, or H2O. This is one of the few constituents whose concentration varies significantly throughout the atmosphere. Almost all the water vapor in the atmosphere is confined to within 10 kilometers of the surface. Whereas the warmest tropical air is about 4% water vapor by volume, in polar regions, water vapor near the surface may be as low as 0.2% by volume. On average, over the whole planet, water vapor makes up about 0.5% of the atmosphere. The next most abundant gas is carbon dioxide, presently making up 410 parts per million of the atmosphere. 1 part per million is equal to 0.00001%. This means that for every 1 million air molecules, approximately 410 of those are carbon dioxide. You may be familiar with carbon dioxide because it's often spoken of in the same context as climate change. In fact, its concentration in the atmosphere has been steadily rising because of human activity. Before the Industrial Revolution kicked off, carbon dioxide concentration in the atmosphere was around 280 parts per million. Carbon dioxide concentration has been measured precisely since 1957 because of the work of John Keeling, with his first measurements being taken from a flask at the South Pole. In 1958, Keeling started the CO2 monitoring program at Mauna Loa Observatory in Hawaii and supervised it until his death in 2005. As a consequence, the curve showing carbon dioxide concentration in the atmosphere over time now bears his name, the Keeling curve. These first measurements showed carbon dioxide levels at around 318 parts per million, already affected by human activity. Carbon dioxide levels typically reach a maximum in the northern hemisphere spring and a minimum in the northern hemisphere fall. This is because of vegetation growth and die-off that occurs seasonally. As of 2020, carbon dioxide levels have reached approximately 410 parts per million above pre-industrial levels of 280 parts per million. During glacial periods, when ice sheets covered much of North America, these carbon dioxide levels were much closer to 180 parts per million. Going back to the composition of the atmosphere, the next 5 most abundant gases are neon, helium, methane, krypton, and hydrogen gas. Of these, neon, helium, and krypton are noble gases and largely unreactive. Only methane is relevant to global energy balance and is again connected with human activity. Its present-day concentration is around 1,800 parts per billion, compared with about 720 parts per billion in the pre-industrial period. Excluding trace species, the remaining gases include ozone, nitrous oxide, carbon monoxide, ammonia, nitrous dioxide, chlorofluorocarbons, or more commonly known as CFCs, sulfur dioxide, and hydrogen sulfide. Ozone is produced from dissociation of oxygen gas from sunlight and as a byproduct of certain near-surface chemical reactions. Nitrogen dioxide is another gas that has been increasing because of human activities. Chlorofluorocarbons are entirely associated with human activities, as they are synthetic molecules that were manufactured starting in the 1960s because of their utility as refrigerants. Among these, human activities can be directly attributed to changing concentrations in many of these gases. The gases highlighted here in red are very important to this class. They are the infamous greenhouse gases, which play a particularly important role in the energetics of the Earth's atmosphere. They include water vapor, carbon dioxide, methane, ozone, nitrous oxide, and chlorofluorocarbons. They are so-called greenhouse gases because they absorb outgoing radiation from the Earth, consequently blocking it from escaping to space. We'll return to discussing these gases shortly once we begin to discuss climate change. Before then, we need to learn a little bit more about the vertical structure of the Earth's atmosphere, namely how it changes with altitude. The Earth's atmosphere roughly consists of 4 distinct layers. From bottom to top, they are the troposphere, stratosphere, mesosphere, and thermosphere. They are distinguished by how temperature behaves in these layers. In the troposphere, temperature decreases with altitude. In the stratosphere, temperature increases with altitude. In the mesosphere, it again decreases, and in the thermosphere, it increases rapidly. These layers are delineated by regions of relatively constant temperature. The tropopause, above the troposphere, the stratopause, above the stratosphere, and the mesopause, above the mesosphere. The pressure is an indicator of how much air is at each level. The amount of atmosphere, or the density of gas in the atmosphere, decays exponentially with altitude from the surface, so that 85% of the total atmosphere's mass can actually be found in the troposphere, or approximately the lower 10 kilometers of the atmosphere. The plot on the right shows the temperature of the atmosphere as a function of height, as well as some of the features you might find within each layer. We'll be doing a deep dive into each of these in a minute. Taking a closer look at the temperature within the troposphere reveals that this temperature is roughly linear. That is, if you were to plot it out on a chart of temperature versus altitude, you'd be able to draw the temperature as a straight line. The change is about 7 degrees Celsius for every kilometer of altitude gained. However, the altitude of the tropopause changes depending on where you are on Earth. The tropopause is around 10 kilometers altitude in the polar atmosphere, 13 kilometers in the mid-latitudes, and around 15 to 18 kilometers in the tropical atmosphere. In the polar regions, the air is cold, dense, and generally tends to sink down towards the surface, pulling down the tropopause with it. In the tropics, violently rising air driven by convection and surface warming pushes up the tropopause, leading to its high altitude in this region. The Earth is pretty unique among our neighboring worlds in the solar system, Mars and Venus. The Earth is the only planet to have a temperature bump associated with the stratosphere. This bump is directly related to Earth's oxygenated atmosphere. Whereas Mars and Venus have atmospheres that are almost entirely carbon dioxide, the oxygen in the Earth's atmosphere can form ozone. The ozone layer, where ozone has its highest concentration, filters out high-energy ultraviolet radiation from the sun, leading to warming where ozone is present. Let's now take a little closer look at each layer of the Earth's atmosphere, starting from the top. The thermosphere represents the edge of space, where temperature is very high and variable, and the atmosphere is barely present. Here, high-energy radiation from the sun, the highest energy radiation that it emits, is absorbed by the atmosphere, leading to very high temperatures of individual molecules. The highest energy radiation from the sun, however, is filtered out by this layer, so it's not experienced by us down in the surface. When solar wind, basically solar gases blowing across space, interacts with the thermosphere, charged particles can be funneled by our planet's magnetic field toward the poles. This can lead to stunning displays of light known as the aurora borealis. Photos of the aurora can obviously be quite striking, and as earlier, I suggest that you go on Google image search to check it out. As we descend into the mesosphere, the atmosphere is becoming more dense and temperatures are increasing. Here, high-energy ultraviolet radiation from the sun can disassociate oxygen gas into its component oxygen atoms, warming the atmosphere. These atoms can then combine with oxygen gas to form ozone through a process known as the Chapman cycle. How much ozone gets formed is a balance between two factors: atmospheric density and available radiation. Higher up, there is more high-energy ultraviolet radiation since it gets filtered out as the closer you get to the surface. However, the atmosphere is also more dense closer to the surface. So although ozone is at its highest concentration at 20 to 30 kilometers altitude, the highest temperatures can actually be found much higher than that at 50 kilometers altitude, at the base of the mesosphere in the stratopause. As we descend into the stratosphere, the concentration of ozone grows to its maximum between 20 to 30 kilometers altitude. This figure here shows a NOAA ozonosonde, a balloon able to make measurements of ozone concentration, flown over Boulder, Colorado on October 3, 2019. The vertical ozone profile seen here in red against the average profile in black. The clear bump in ozone concentration, around 25 kilometers, it shows the presence of the ozone layer. Temperatures drop through the stratosphere as less radiation is absorbed by the atmosphere, as the atmosphere becomes more dense. Since temperatures decrease with altitude here, cold air is naturally sitting beneath warm air. This is a stable configuration of air, the opposite of a pot being heated from below. Recall what happens when you heat a pot from below. That warm water near the bottom circulates upwards, creating boiling water or convective plumes within the pot itself. However, in the stratosphere, since it is the top of the fluid that is warm, it is naturally stabilized against any sort of overturning motions like that. Vertical motions in the stratosphere, consequently, are essentially negligible, as air is unable to move up or down. Because of this, it's very difficult for air in the troposphere to move into the stratosphere. Once it does, it is unable to rise any farther without encountering a warmer environment. And if cold air is in a warm environment, it will tend to sink back down. So that tropopause then is a natural boundary that effectively locks gases within the troposphere. The lowest layer of the Earth's atmosphere is the troposphere. As mentioned earlier, here in the lower 10 to 18 kilometers of the atmosphere is where we find 85% of the atmosphere's mass and essentially all of the water vapor. Most of what we recognize as weather is generated here because of how water is pushed around by the atmosphere. In the troposphere, rising plumes of air from heating the surface or cooling of the upper atmosphere can cause strong vertical motion, much like a boiling pot. Most of these air parcels only rise midway through the troposphere, but some can rise all the way to the top. Because the stability of the stratosphere largely restricts air from being able to move through the tropopause, rising air that hits the tropopause instead spreads out laterally. We can see this clearly in the form of anvil clouds, which are formed by particularly strong vertical updrafts and air that condenses to form cloud droplets and impacts the tropopause. The flat air at the top is where this air hits the tropopause and cannot rise any farther. Air in the troposphere is circulated globally through what is known as the general circulation. These natural circulation patterns arise because of a combination of non-uniform heating of the Earth, that is, warmer temperatures at the equator and cooler temperatures at the poles, and the rotation of the planet. They are also the primary drivers of large-scale weather events, and are important for keeping the polar regions warm, even in their dark winter months. We'll revisit these patterns again later in class. There are a number of fantastic videos out there that clearly show global atmospheric dynamics in the troposphere, and how important these large-scale systems are for redistributing air around the planet. We'll look at these videos more closely in the future, as it shows how carbon dioxide and carbon monoxide, often coming from human sources, recirculate through the global atmosphere. But you can always check out the YouTube link in the meantime. Okay, that's plenty for today. Now that we understand the structure of the Earth's atmosphere, we can look back in time and understand how it's changed over the past 500 million years. Talk to you next time.